higher disturbance level. Instead of putting a strict emission limits on individual customers, generating and non-generating customers, the choice of planning level and other objectives can be re-evaluated. This is a sensitive issue because it increases the probability of electromagnetic interference. That is the equipment damage or malfunctioning due to high level of voltage disturbances. Before we discuss the way of allowing the disturbance level, so it is good to have a look at a complete framework shown in the figure. So this is the figure. So the ultimate aim is to ensure that equipment is connected to the power system grid, so works as an intent or stated in IEC standards to ensure a high probability that electromagnetic compatibility is achieved. The reference level in the figure could be an electromagnetic compatibility level according to IEC standards. Voltage characteristics according to EN 50160 are the highest permitted level set by the local regulators. The reference level is chosen in such a way that the immunity of the equipment with higher probability is higher than the reference level. The requirements on the equipment's immunity are set in an international standards and they are difficult to change. It is however the network operator's responsibility to keep the disturbance level below reference level. To be able to ensure this, network operators is putting requirements on emission from individual customers connected to the grid. During the design of the network and when assessing the connection of new customers, the aim is to keep the disturbance level below planning level. There are indicative value for this session, that is IEC technical reports, but it is in the end it is up to each network operators to set appropriate planning levels. The planning levels are always chosen below the reference value so that to have a safety margin covering and among other uncertainties in calculations module. In our future growth, emission and emission from all the customers to which the no emission limits can be allocated. The amount of emission allowed for given customers is determined from the planning level using some kind of allocation algorithm. For individual devices, the limits are set in IEC product standards and in other standard regulations. From the above figure, it is clear that the raising the planning level or using the allocation method results in higher emission limit will not only immediately result in widespread interface. So there are sufficient margin between the difference level and the interference occurs only when the actual disturbance level exceeds the actual immunity of that device. Raising the planning level, however, immediately allocates the more space for the emission by these individual customers and devices. This would simply the connection of new industrial installation and the connection of distributed generation. So some network operators use rather strict and low planning levels and may be very reluctant to raise them. The reason for this is that they have to ensure the disturbance level which does not exceed the reference level. So this will reduce the risk of interference, but it could result in excessive burden on the emission side. This in turn could be a barrier to the introduction of new renewable sources of generation. An important point of any discussion is that raising the planning level or emission limit is the question of who carries the risk. All those things has to be considered. And also when the reference level is exceeded, what to do. So all those things has to be considered. So when this risk is carried solely by the network operators, the incentive to the rise of planning level will be obviously very small. The next step to consider is related to increase in the reference level. So this is more difficult because it probably requires a changing in international standards on electromagnetic compatibility and also voltage characteristics. There has been strongly an objection to this from many sides. So allowing the reference level to be raised when standard actual disturbance level becomes high. So this would remove any incentives for network operators to improve their network. So the various power quality and EMC standards are coordinated such that a well-designed grid and well-designed customer equipment would with a high probability will result in the electromagnetic compatibility between the equipments and the grid. Here the setting of compatibility level and other reference level in turn is based on the trade-off between the cost for the improvement of this immunity and the cost for the improvement of emission, even with the introduction of distributed generation. So this would be a basic rules that holds for the introduction of large amount of distributed generations. However, require reconsideration of various limit. The first change in the emission takes place at a frequencies that were not concerned before the interharmonics and even harmonics. Here high frequency harmonics are slower voltage fluctuations. The reference level for these are either low because it was easy to reduce the emission, or no limits exist at all because the disturbance was not seen as concern. The introduction of large amount of distributed generation will result in increase in the levels of interharmonics and even harmonics, as those the harmonics were rarely emitted, and in the past the introduction of large amount of distributed generation will result in the increase in the level of interharmonics and even harmonics. As those harmonics were rarely emitted in the past, the reference level are low and can be easily exceeded. The same will occur if the reference level for the distortion above 2 kHz are exploited for 1 below 2 kHz. In fact, more and more consumers, electronics and lighting equipments are also generates the interharmonics and high frequency harmonics. Also for triple harmonics, the disturbance level now exceeds or come close to reference value. In many cases, even in existing grid without distributed generation, the discussion on the choice of reference level. So therefore it's a concern for a distributed generation which remains unknown. Being careful has to be one has to be careful to larger extent guiding principle when setting a limit that is setting the limit for voltage distortion somewhat below the highest level, which is measured at a location where there is no problem were reported. So investigations are needed to decide, for example, if it is reasonable to set a more strict limit at 370 Hz than 350 Hz. So in 50 Hz system. These are the some of the important key points what we are discussed with respect to higher disturbance level. So let us see the passive harmonic filters. Passive harmonic filters. Passive harmonic filter consists of inductance and capacitance and sometimes resistance. The two most commonly used configurations are the series filter and high pass filter. The series filter consisting of inductance and capacitance that creates a low impedance for harmonic current at a single frequency. The filter is typically tuned at close to an harmonics, that is 5th, 7th or 11th and 13th. So the passive high filter containing also some resistances, so which creates a low impedance for all the frequencies above certain cutoff frequency. The cutoff frequency is typically rather high, above 15th harmonics. To prevent the increase in the losses at the power system frequency, the passive series filters can be used in all the cases where the voltage distortion for individual frequency otherwise becomes too high. So this is most likely not due to emission from the distributed generation, but more likely to this harmonic resonance or a weakening of transmission grid. Passive high filters would be a possible solution to high frequency distortion. The disadvantage of passive series filter is that capacitance of the filter together with the source inductance that creates a parallel resonance. With high impedance to a lower frequency, this may require some additional filters for lower harmonics and as shown in a problem with a broadband. Mitigation of equipments is based on power electronics converter, which has an high potential to improve the power quality, and the static wire compensator and STATCOMs have been successfully used to mitigate the voltage fluctuation. Such converters can be installed at a central location in the system, for example to limit voltage fluctuation in weaker front of transmission grid close to the source of voltage fluctuations like wind turbine. Converters based on voltage source converter can also be used to mitigate the harmonic distortion as long as the switching frequency is sufficiently high. A whole range of algorithms are being discussed to mitigate the voltage distortion without the need to know the current emission. Such equipments could be installed at a central location in the system. Commercially available equipment still is based on the open loop control. When the injected current compensate the measure current, so the use of such equipments will limit the location close to the source of emission. Power electronics converter, which is based on voltage source converter technology, are more and more used as a grid interference for distributed generations. Examples are the inverter with micro CHP, or the solar power and full power or partial power or inverter. The same algorithm for mitigating the voltage fluctuation and harmonic distortion can also be implemented in series converter. An interesting application that becomes being discussed in the literature to implement the selected frequencies. At these frequencies, the converter behave like a resistance in providing a damping in case of the harmonic resonance. Such an approach would be relatively simple to implement because no additional hardware is needed. So the requirements on the accuracy of the algorithm, like the frequency tuning, do not have to be high because the damping is provided by many individual customers. So the occurrence of the resonance cannot be prevented in this way, but by damping will reduce in resulting in voltage and current distortion. So by using this power electronics converters, we can mitigate the distortion in the voltage and current, but damping will not reduce. Okay, so with this we move on to reducing the number of dips. Let us see that okay. In reducing the number of dips, so The mentioned increase in the number of dips due to weakening of transmission grid is a separate issue for the most of the mentioned solution, which does not hold. It should be first to be note that no reference level exists for voltage dips. There are no limit on what is the acceptable number of voltage dips that are going to happen. The first solution is to increase the number of dips. That would be just refer the lack of any standards and simply accept it. So this would put a risk completely to those customers that are sensitive to the voltage dips. Typically, large industrial installation connected to the subtransmission transmission grid. So there are, however, a number of ways to mitigate the voltage dip due to the independent of what caused the dip. So here let us see what are the number of ways in which we can reduce this number of voltage dips. So one is by reducing the number of fault or reducing the percentage of fault involving more than one phase. There are many different ways of achieving this, like shedding the wire, animal protection, and replacing the lines by cable. Apart from cost, this is and often one of the best solution, and also we limit the spread of dips by changing the way in which the grid is operated. Limiting the number of line connected to the substation, limiting the number of parallel lines, and open loops are some of the good options for reducing the voltage dips. The disadvantage with most of the solution is that the grid will become weak. The reliability and stability of power quality causes some problem regarding this. So the cost of such solution could be, however, it is low only. Reducing the fault clearing time by using fault protection is also a good method of reducing the voltage dips. So this often, but it could result in the risk of production or maltrip, with the consequences of that reliability and operational security. And also we can installing the mitigation equipment such as local energy storage to allow the installation to the read through the dip. So also microgrid with possibility to get very quickly into island operation have been mentioned as a solution, and also by improving the immunity of the equipments in the installation of industrial process against voltage dip.